So I'd like to welcome you to the Harry Lipkin Memorial Colloquium. Introducing Harry will be Yossi Neil, so I won't do it myself, and I'll just introduce Yossi. So Yossi started his studies some time ago in the Technion as an undergrad student, and then he moved here. He did his master's with Adam Schwimmer, and then moved to PhD with Chaim Harari. During his PhD, he went for some period in the SLAC in Stanford accelerator, and that's also where he did his postdoc afterwards, and came back to join Weizmann in 1990. Here ever since, and last summer he finished his serving as the dean of physics, and I guess now that gives us time to teach us and explain to us about the last Nobel Prize. So thank you.
Harry Tzvi Lipkin was one of the founding fathers of this faculty when it was still the Department of Nuclear Physics in 1954, and one of, I would count, two founders of theoretical particle physics in Israel, which is my field, and a colleague and a friend. And this colloquium is, he passed away 3 months ago, and this colloquium is dedicated to his memory. I think that the one word that for me describes Harry in everything he did was he's a pioneer. He was a pioneer in his life, in his career, in physics, took risks, did not hesitate to take new avenues in whatever he did. Spectacular life story. I will not tell it all. Now, there's a problem here. This does not change at all. So he won the Emet Prize in 2002 and the Wigner Medal and various other honors. And you can read, if you're fast, the jury statement on the left to learn of his scientific achievements. Oops, no. And okay, on the right there is his life story. So while these things are running here, I'll tell you that he was born in 1921 in New York, did his undergraduate in Cornell University in electrical engineering. Then he stated that engineering is for those that want to solve today's problems, but if you want to solve tomorrow's problem, then you must study physics and not engineering. In the meantime, World War II was there, and he worked in MIT in developing an anti-U-boat microwave radar, which was a significant project for World War II. Then he went and did his PhD in experimental physics in Princeton, immigrated to Israel, joined Kibbutz Sasa, did together with Malka, his wife, who is sitting here, made a huge financial mistake by leaving Sasa. You may know that he's now the richest kibbutz in Israel. He could have become a millionaire. Instead, he became a physicist. Came to Rehovot, was sent to France to study nuclear reactors, came back with this knowledge and did what he did in that field. And then he co-founded in 1954 the Department of Nuclear Physics, which is now the Faculty of Physics. And as mentioned in this beautiful obituary that you are invited to read in Stern Courier and also in Physics Today by Harari and Karliner, all of this until the age of 34, and there are 60 more years of a glorious career in physics. It's not good? Okay.
I can do it.
Okay, so my connection, I was here a student. I took phenomenology course with him, the course that now I'm giving here. I have to say that he was a much more pedagogical and good writer of books than he was a lecturer in courses. But still, his enthusiasm was very attractive and catching. And he was the advisor of Chaim Harari. So Harari was Lipkin's and Yuval Ne'eman student. Here is a paper, Group Theory, what we do until today, from 1965. Then some 26 years go through, and he writes a paper with Chaim's student, that's me. The term grant student, I did not invent it. That's how he called me in his correspondence with me. He managed 6 years later to write a paper with a grad student, Yuval Grossman, who was mine, and continued to communicate and write papers until we wish that all of us would be able to write relevant papers at the age of 90-something, which he did. Preparing for this colloquium, I have a lot of emails over the years with Lipkin. He was commenting about everything, politics, education, physics. Actually, he was a blogger well before the word blog was invented. And I read and was fascinated by some of the things and what he says about the government. This lecture is recorded, so I will not quote all of his emails here. But here is one thing that he told about the beginning of this faculty, which I think is very important for our culture, as it still goes on today. So most of you are not aware of our revolution at the Weizmann Institute. At that time, that's 1954, all other departments at the Institute were led by department heads whose name appeared on all papers by their students. The department heads built empires in which their students continued to work under their direction. We with Yigal Talmi and Tzvi himself, we strongly opposed this tradition and broke it vigorously. We were doing our best to create the future leaders of the Institute and of Israeli physics. We wanted them to have the best opportunity as postdocs to work with the best places in the world and also have contacts with the best other students who would later become the leaders of physics in their own countries. I think this, as far as I can judge, is still the culture here. We are still not building empires, but trying to give our students the best opportunities that they can have. Tzvi had a wonderful sense of humor. He was free of any aspect of arrogance or anything, and he had a lot of self-irony. And he was one of the two founders of the Journal of Irreproducible Results, which has wonderful satirical and humorous papers in it. He was one of the inspiring figures as a result of that of the Ig Nobel. He's actually an honorary member of the Board of Governors. And in our correspondence, I found just one typical email of the way that Harry was reacting to things. Probably you cannot read it, so let me tell you. Shalom Uri, I think that it is disgraceful that we have not had a decent printer for a year. If the Weizmann Institute does not have the funds to provide a decent printer for the top floor of the particle physics department, we have now one, but it's okay. I will happily, after I receive the Emet Prize, donate from my prize money whatever is needed to give us all printer that works. Of course, I will demand that a plaque will be placed over the printer stating, this printer was provided by the generosity of Harry Tzvi Lipkin Foundation. That's not untypical of him. So you will not be surprised that among the many, many emails that I read, the one that somehow touched my heart and made me actually excited is an email from him to me, 2006. Shalom Yossi, I enjoyed your colloquium on neutrinos very much, which is the same topic that I give the colloquium now. So I think that with such a recommendation to all of you to enjoy the colloquium, I will move on to the colloquium. I think also Harry, as far as I knew him, would say, stop all this nonsense, let's talk physics, and would ask me to start a colloquium. So this is what I'll do now. And this colloquium is about the recent Nobel Prize. So on the left, we see Takaki Kajita, a Japanese professor from the University of Tokyo, and his experiment, SuperK. We'll come back to the experiment. And on the right, Arthur MacDonald, a Canadian from Queen's University, and his fantastic experiment, the Sudbury Neutrino Observatory, SNO. And it's interesting, they both got their Nobel Prizes for experiments not that started a research of something. The research on the topics of atmospheric neutrinos and of solar neutrinos was started well before. Other people found that there is a puzzle, and they got their Nobel Prizes, the two respective people, in 2002. These are the two experiments that gave a conclusive answer as what is the solution of the puzzle, and this is what I'll try to explain. What was new, what was unique about these experiments, and how did they answer the puzzle in a strong way. By the way, these are the 5th and 6th neutrino experiments to get a Nobel Prize. So if you want a Nobel Prize, maybe experimental neutrino physics is the way to do it. I believe, indeed, that these are not the last neutrino experiments that will get it. But part of it is that the neutrino particles never stopped surprising us. I mean, they have a very rich career of giving us surprises all along. All these 6 Nobel Prizes are well deserved, and maybe a few more should have been given along the way. Even the start of neutrinos in human knowledge is somewhat unusual. Usually, an idea or discovery start either with an experiment or with a theoretical paper. This is not the case here. The neutrino appear first in human knowledge in a letter, famous letter, written by Wolfgang Pauli, 1930, to the participants of a conference in Tübingen, in Germany. There was a puzzle, radioactive decays. What you see is the final nucleus and the electron. If these are two-body decays, then you know what the energy of the electron must be. And there was a continuous spectrum. So it seems that conservation of energy is broken. And indeed, some people in the community, including Niels Bohr, were willing to state that that's what's happening, that the law of conservation does not apply in radioactive decays. And Pauli instead suggested in this letter written in German, but I have here an English translation, suggested another solution, a particle that is not detected by the detector and carries the missing energy. So the law of conservation of energy is saved at the price of having a particle that is not detected by the detector. And there are here, I mean, there are here some very interesting statements. I do not dare to publish anything about this idea. He was very embarrassed by his own idea. I admit that my remedy may seem almost improbable, but nothing ventured, nothing gained, and the seriousness of the situation, due to the continuous structure of the beta spectrum, is illuminated by a remark of my honored predecessor, Mr. Debye, who told me recently in Brussels, "Oh, it's better not to think about this at all, like New Texas." Okay, I don't know, sense of humor. And he asked the participants of the conference to judge this idea. And I mean, as I said, there are here many interesting statements. For me, the most intriguing sentence here is one that usually goes unnoticed, so let me read it to you. Unfortunately, I cannot personally appear in Tübingen since I'm indispensable here in Zurich because of a ball on the night from December 6 to 7. Now, in my many years in physics, I think I know hundreds of physicists, and no offense to anyone, I'm not sure that any of them can be described as indispensable in a ball. Okay, that's not usually what characterizes physicists. So Wolfgang Pauli must have been a special person. Later he said about this letter, I'm afraid I did a terrible thing. I postulated a particle that cannot be detected. And on this he was wrong. Never took 26 years. And in 1956, that's one more thing. This picture of Pauli is taken in the University of Copenhagen, which later became the Niels Bohr Institute. And this year, many of us here, including myself, lectured in the very same place. And they preserved the Danish very nicely, the same board, the same extremely uncomfortable seats. It's benches, yeah, you have to sit. But it's all there, and it was quite exciting to know that we are in such a nice place. So 1956 is the start of the experimental career of neutrinos. That's the discovery by Reines and Cohen. Reines got the Nobel Prize in 1955. Cohen did not because he was dead at that time. And the detector was 200 kilograms of water close to a nuclear reactor, which emits a huge flux of electron antineutrinos. And these antineutrinos interact with the protons in the target, produce a positron, which soon annihilates with an electron. That gives 2 photons. In addition, the neutron excites a cadmium. This water were enriched with cadmium, and then there is a third photon 5 microseconds after the first simultaneous 2, and these 3 photons are a signal of this interaction and the proof that the electron neutrinos are there. They were very happy about the results. They wanted to tell Pauli that they found it. At that time, no email, no archive, so I think many of us still remember that there were telegrams. So they sent a telegram immediately to Pauli. We are happy to inform you that we have definitely detected neutrinos from fission fragments by observing inverse beta decay of proton, and observed cross-section agrees well with expected. And it says that Pauli replied to them with a telegram saying everything comes to to those who know how to wait, which is actually a quotation from Tolstoy. So I don't know, I wait. I'm hoping that... So that's the start of neutrinos, and I'll here describe first what are neutrinos, what are their special properties, and I'll argue that these properties have an advantage and a disadvantage, and the same properties, and the advantage makes them wonderful messengers from dramatic events all around the universe up to its edge, but on the other hand, makes them also very hard to detect and requires very unusual detectors, as we will see. Then we will describe the phenomena of flavor transitions, and I will explain that what these two experiments observed are actually two distinct phenomena: neutrino oscillations and the MSW effect. That's for atmospheric, that's for solar neutrinos. I'll explain both. The SuperK experiment of Kajita detects atmospheric neutrinos. This SNO experiment of McDonald's solar neutrinos. And finally, while all of this is important and interesting, it has implications for both particle physics and for cosmology, and I'll try to explain everything. So, what is the neutrino? This is the latest addition to neutrino experiments. This is the ice cube experiment taking place at the South Pole. What we see here is the laboratory above ice, and this is actually the detector. Its effective volume is 1 kilometer cubed of ice. So this is gigaton of ice. This is, I think, the biggest detector ever. And these are strings. Along the strings, there are photo detectors. And the start of this is 1.5 kilometers underneath the ice, and the bottom is 2.5 kilometers underneath the ice. And it's really an amazing story, and I'll mention it later, but this is the latest and perhaps another future Nobel Prize. So what are neutrinos? We characterize elementary particles by spin, mass, and their interactions under strong, weak, and electromagnetic interactions. So neutrinos are fermions, spin half. What is their mass is a major question on this that these experiments have answered, at least partially. And just I'll add that we had reasonably good reasons to think that they are massless. Okay? I'll come back to that later. And what's special about them is that unlike any other elementary matter particle, they have no electric charge, and therefore they are insensitive to the electromagnetic force. They have no color charge, and therefore they're insensitive to the strong force. And they have only weak interactions, and that will play a crucial role in this talk. But these two things, that they have neither electric charge nor color charge, or insensitive to electromagnetic and strong forces, this is what makes them elusive. Everything in the universe is more or less transparent for them. So just to illustrate this, neutrinos are, so the main burning of the sun is at the core of the sun. And it produces, among other things, photons and neutrinos. Both are messengers from the sun. We've seen sunlight or photons for many years. For a photon that is produced in the core of the sun to reach the surface of the sun, it takes about 100,000 years. By that time, it loses all the original information about what happened at the core. Not the energy, momentum, direction, everything is changed. Neutrinos that are produced in the core of the sun is transparent from them. They are here after 8 minutes after production. That's the distance between us and the sun, speed of light. And they retain their original energy, momentum, direction. There is one thing that they do not retain, which is important for this talk, but everything else is. And so if we look at photons or sunlight or at neutrinos as messengers from the sun, it's only neutrinos that allow us to understand or to test our ideas of what is happening at the core of the sun. So that's what makes them wonderful messengers, and we are looking for them from many sources in the universe, as I'll describe in a minute. On the other hand, also Earth is transparent to them. So how do you stop them? How do you interact with them? You must build huge detectors, and you must bury them deep underground so that no other more abundant particles that do have electromagnetic or strong interactions mimic the signals and screen the few neutrino interactions. So all of these will play a role. But this is the spectrum of neutrinos from all sources that we know in the universe, or for most sources. So on this axis is the flux in units of second to the -1, centimeter to the -2. Just important to understand that we span here 50 orders of magnitude in flux for the various sources. On this axis, there is a logarithmic scale of the energy, and it's from 10 to the minus 15 to 10 to the 11 GeV, so 26 orders of magnitude in energy. The cosmic neutrino background, these are neutrinos that decoupled from the rest of the plasma when the universe was about 1 second old, and they have information about the universe at 1 second after the Big Bang. Solar neutrinos are here, so this is growing energy, but reduction in flux. The supernova 1987, atmospheric neutrinos, neutrinos from cosmic ray sources, and something called GZK neutrinos. I'll come back to this. So, by the way, this we tried to look for this plot in the literature, and with the advice of my advisors, my student Ayelet Efrati and Kfir Blum, who is here, and Eli Waxman, the understanding was that there is not even one plot in the literature that is correct, or fully correct. So I had to draw this on my board. And since this is now the only copy in the world of a correct spectrum, then I do not dare to erase it from my board, and I cannot write anything else. So research is paralyzed until I give up on this. So now we'll see how we look for all these parts and where we are with the two present experiments. So here is a reminder. The cosmic neutrino background are the most abundant. There are 330 of them in each centimeter cubed of the universe, but they're also the least energetic. Their typical energy is 10 to the minus 4 electron volt, which makes it extremely difficult, if not impossible, to detect. So we know that they are there because the wonderful agreement between theory and the observation of the cosmic microwave background radiation requires that these neutrinos are there, and in the quantity that is close to 330 per centimeter cubed. So they must be there, but we want to observe them and see if their properties indeed match what we think. And now there is a daring prototype experiment in Princeton that claims that it will be able to do it. This Ptolemy is acronym like everything else in high-energy physics. It's Princeton, Tritium, Observatory, and I don't remember the rest. So maybe in the future. I did not mention here, sorry, it's important in the previous transparency. Whatever is in solid line is things that have been detected. The dashed lines are the things that are yet to be detected and hopefully will.
Question, is it possible to ask questions?
If they are urgent, yes.
Why is this graph of cosmic
Micro.
background shows that there are neutrinos?
Well, all you can be impressed here is that the blue dots, which are observation, and the red line, which is theory based on some best fit parameters, match wonderfully over really a huge amount of data. But it's not explained here, just for impression. On the other hand, the most energetic, really imaginary high energies, 10 to the 21 electron volt, are the GZK neutrinos. So cosmic rays hit the atmosphere. There is a resonance about 10 to the 20 and electron volt, which cuts off the spectrum of cosmic rays. But we expect that neutrinos will come out as a result of this interaction, and we want to see these the highest energy neutrinos. And for that, another experiment in the South Pole is being built here. The problem is the low flux. The energy is high, but the flux is extremely small. Another part of the spectrum here are neutrinos from cosmic ray sources, which we don't know what they are. We want to study what they are, maybe gamma ray burst or within starburst galaxies. This is a picture of one of the galaxies that is start forming. And probably these are the detectors that have been recently discovered by IceCube. So this part here, which starts changing from dashed to solid. We see here there are a few tens of events from about 4 or 5 years of operation of the IceCube experiment. They are given here. And I must mention that the prediction of Weizmann and Bacol, which was also the reason to build a kilometer cube experiment, is given here in this line, which matches wonderfully the observations. So this is the start of a new field, observation of neutrinos from cosmic ray sources. Supernova, MEV or tens of MEV neutrinos, was observed essentially once in 1987 by 3 experiments in Japan, United States, and Russia. Very famous 22 events, 22 neutrinos from, this is supernova 97A as it's seen now. This is the present picture. We learned a huge amount of information from that, but we are much better prepared for the next supernova. When it will come, we'll have the same distance, say, or similar distance, we will have thousands of events, and we will learn much more. And it should have already happened, but it doesn't, so it's a statistical thing, but we wait, and everything comes to those who wait, so let's see. And finally, solar and atmospheric neutrinos. This is the topic of this talk, of the two experiments. And what we see here is an amazing thing. It's a picture of the sun in neutrinos. Okay, that's a new thing. For us physicists, it's exciting that you can have a picture of the sun in neutrinos. And one of the interesting things is that, unlike sunlight, you see the sun in neutrinos both at daytime and nighttime because Earth is transparent to them. And because of special effects have to do with Earth, the sun is brighter in the night in neutrinos than it is in the day. A little, by 3% brighter. So it's just an exotic fact. And I'll explain what these neutrinos are and what they told us. So, flavor transitions. This is a picture taken from the Nobel Foundation description of these Nobel Prizes. We see here an electron neutrinos thinking of what to dress when I come to the detector on Earth. Should I dress like a mu neutrino or tau neutrino or remain an electron neutrino? This is what I will try to explain now. So we come back to the weak interactions. There are two types of weak interactions that neutrino can undergo. They can exchange with the detector, with protons, with whatever neutral weak force carriers, the Z boson, and they remain whatever they were. Electron neutrino exchanging a Z boson with a proton remains electron neutrino, mu neutrino, tau neutrino. Oh, maybe I should say there are three types of neutrino, and we define them by the weak interactions. Okay, so not by the Z exchange, but by the charge for carriers of the weak interactions, the W. This is how we define these three types that we observe in our detectors. So electron neutrino, by exchanging a W, is the neutrino that becomes an electron. Mu neutrino is the one that becomes a muon, same charge, same absence of color charge as the electron, just 200 times or so heavier, and still heavier the tau. So neutrino tau is defined as the one that produces a tau lepton by exchange of the W. So we define the three types of neutrino, electron neutrino, mu neutrino, and tau neutrino, by their charged, by the weak interactions exchanging a charge force carriers, the W, okay, by what they produce, electron, mu, or tau, respectively. However, if they have a mass, then there is a second way to characterize them, which is by their mass. Okay, so there are two ways to characterize them, either by their weak interactions, what they do when they exchange a W, or by their mass. And these two are not the same sets of three particles. Each of them is a superposition of the other three. Okay, so the electron neutrino is a superposition of neutrino 1, 2, and 3, the three neutrinos with well-defined masses, if they have masses. Similarly, mu is another superposition. So these are two different bases. The mass basis, which is characterized by well-defined masses, and the interaction basis, which is defined by what they produce when they exchange a W with their target. So two bases, there is a transformation between them, a change of basis, a unitary transformation. There will be a bit of mathematics on the next transparencies. For massless neutrinos, or more generally, if they were degenerate, then the flavor eigenstates, these interaction eigenstates, are the same as the mass eigenstates. But for massive neutrinos, these are two different bases. So here is the mathematical formalism. It's really simple. By the way, Tzvi worked on this a lot, and his paper with Yuval is about exactly these things. So a flavor eigenstate, say Ni, is some combination of the mass eigenstates. There is here a unitary transformation that transforms between these two bases. So let's say you produced a certain interaction eigenstate at distance 0. Then it traveled the distance L. Each of the mass eigenstates has its own frequency change when it propagates in distance, exponential of I, the momentum, and the distance L times Ni I. So the original combination is changing because the three mass eigenstates have different frequency, if you want, for the waves when they propagate. All these neutrinos are always relativistic, and so the difference in their momenta is due to their small masses, which are much smaller than the energy. And then you ask, suppose I produced, say, electron neutrino or mu neutrino at the source. What's the probability that I will see tau neutrino at the detector or whatever at the distance L? And a two-line exercise gives you some expression, which is a bit complicated. But if you think of only two neutrinos, which actually is a good effective description for all the experiments that I'll describe, each of them has two other neutrinos playing a role, then a unitary 2 by 2 matrix has just one parameter. So So it's just sinus theta is the rotation from flavor basis to mass basis. There is a single mass square difference between two mass eigenstates. And for example, the probability that a mu neutrino was produced in the source and a tau neutrino was observed at the distance L, in detector at distance L from the source, is this simple expression, sinus squared 2 theta, sinus squared delta m squared L over 4e. So the probability of a change of flavor is oscillating with distance. That's the source of the name neutrino oscillations. Okay, there is an amplitude, sinus squared 2 theta, but then as a function of L over E, it goes, okay, when L equals 0, the probability of a change is 0. And then it grows to sinus squared 2 theta, goes back to 0, and again. These are neutrino oscillations. So that's one phenomenon of flavor transition. Then there is a second one, a bit more complicated, but still basic quantum mechanics, things that you could do in your undergraduate studies if you were asked in an exam to do it. That stands from Wolfenstein, Mikheyev, and Smirnov, the three people that understood what's going on. So when the neutrino is moving in a very dense plasma and interacting with it, then there is also a coherent forward scattering where the scattered and unscattered waves are coherently interfering constructively. And that can be described as an effective mass that adds to the neutrinos. Okay? So this interaction, if you want, keeps it slower than the speed of light and gives it an effective potential. And this effective potential, it's weak interaction. So G Fermi is the coupling of the weak interaction. And in a plasma, like in the sun, which has protons, neutrons, and electrons, then the difference between the effective potential and electron neutrino and of the other neutrinos, due to the fact that the sun has electrons but not muons or taus, is proportional to the number density of electrons. And you can incorporate this in an effective mass squared matrix. And the important thing is here on the diagonal, there is a mass square difference, but there is also exactly this effective potential difference. And so if an electron neutrino is produced at a very high density of electrons, it gets an additional mass. Okay? It becomes heavier than it is in vacuum. Okay? And if the number density of electron is slowly decreasing, as it is in the sun from the core to the surface, then this addition to the effective mass is going smaller and smaller and smaller. And when it gets to the surface, it has its original mass, whatever it is. Okay? So that is the thing to remember. And now we see a typical two-level system that you solve in your quantum mechanics. So this is really quantum mechanics in the sun, quantum mechanics in various environments. Electron neutrino is produced in the core of the sun, very high density of electrons. So it is produced as the heavier mass eigenstate, to an excellent approximation. Then it goes slowly out, or quickly, close to the speed of sun, out of the sun. At some point, the other neutrino has no electrons, so the other mass, or mu neutrino, say it's a flat level here. And the two levels reject each other. And then if the transition is adiabatic, and it is adiabatic in the sun, this is a question, quantitative question, it remains on the upper branch and comes out of the sun, not as an interaction eigenstate, not as the electron neutrino, but as the mass eigenstate, the heavier mass eigenstate. Now, coming out as a mass eigenstate means it doesn't oscillate anymore. Okay? So electron neutrinos produced in the sun, if all of this really happens to them, do not oscillate between the sun and the Earth. They come out as a mass eigenstate and reach Earth as the mass eigenstate. And then the probability that we will be observed as electron neutrino is the projection of these heavier mass eigenstates on electron neutrinos. How much electron neutrinos there is in it. So these are the basic things to remember. By the way, Wolfenstein was the first to think about this effect in matter. And he made a sign mistake. And he thought that the sign here and here is negative, which made it a bit uninteresting to the community because it doesn't produce any interesting effect in the sun. And Mikheyev and Smirnov both corrected sign mistakes. So sign mistake, which we do all the time, are sometimes important in the impact of our papers. And they also were the first to apply it to the sun and understand what it means. Okay, so now to the experiment. First, the experiment for atmospheric neutrinos, SuperK. What we see here is the detector of SuperK. The height of this detector is about 15-story building, okay, some 40 meters or so. This is 50,000 tons of water. It's surrounded by photomultipliers. And the way you put them and the way you clean them is filling the water here slowly, slowly. Then 2 or 3 students in a boat go around, clean one detector after the other, or glue them there, finish, a bit more water, the next layer, a bit more. I never ask what happens when water reaches this level. I hope that the effects are not to the trapped students there, but we'll see. So what are atmospheric neutrinos? Cosmic rays hit the atmosphere. They produce, in the end of cascade decays or whatever, a lot of pions. Pions decays to muons and muon neutrinos. The muon decays further to electron, electron neutrino, and muon neutrino. That's the source of atmospheric neutrinos. Okay? Interaction of cosmic rays with the atmosphere. There is a total flux of neutrinos, electron and muon neutrinos. The total flux has, we know to calculate, but it has large uncertainties. The fact that the decays of pions eventually give 2 neutrinos or antineutrinos of muon type and 1 of electron type, so the fluxes of muon neutrino and electron, there is a ratio of 2 to 1, is known quite well. Okay? With small uncertainty. But the thing that we know most precisely is the following. We know that cosmic rays are isotropic. They come from all directions. We know that experimentally because we observed the cosmic rays, and the anisotropy is of order 10 to the minus 4, which is irrelevant here. If the cosmic rays are isotropic, the result of that is that if we look at a solid angle, say, above, there is a certain flux coming, and then the same solid angle, 180 degrees below, we should see the same flux in each flavor separately. That's the result of the isotropy. Okay? Above, below, or to the left, to the right, you rotate by 180 degrees, you get the same flux. And this has no uncertainties in it, and that's important for a Nobel Prize. Okay. Fine. So the first experiment to look at atmospheric neutrinos is Kamiokande, which is the predecessor of Super Kamiokande, same mine. Kamioka is the name of the place in Japan. NDE stands for Nucleon Decay Experiment. This experiment was built to find proton decay, or to search for proton decay. Nothing to do with neutrinos. However, these atmospheric neutrinos, when they reach the detector, mimic an event of proton decay. So they are background. Okay? This is a Nobel Prize eventually for a background. Okay? For a background. You have to understand your background if you want to understand if you see proton decay or not. So that was the reason to look at atmospheric neutrinos. And actually, Koshiba, the leader of this experiment, got the Nobel Prize in 2002 for establishing neutrino astronomy. And what the experiment found is that the ratio between the flux of muon neutrino and electron neutrino is 1.2 instead of 2, 60% lower. Now, the problem could be the experiment. The problem could be our understanding of cosmic rays. And the problem could be that we do not understand the features of neutrinos in a precise way. Okay? Boring, semi-boring, exciting, and as usual, the particle physics community is skeptic and waits for something which is more definite. So then comes the Super Kamiokande experiment. The Kamiokande experiment had 5,000 tons. That was not enough for statistics and various other purposes. So you go down the mine. Okay, this is a mine, some kilometer underneath Earth. Helmets, elevators of miners, all of these things. And instead of 5,000, you put there 50,000 tons of water. And the things that are important is that for each neutrino event, this experiment can measure 3 things. The direction. Now, direction is distance here, because if a neutrino comes from below, it means that it came from the atmosphere on the other side of the Earth. So it traveled about 10,000 kilometers. If it came from above, it traveled about 20 kilometers in the atmosphere. Okay, so there is a range here of some 3 orders of magnitude, depending on direction of how much the neutrino traveled before arriving to the detector. It can measure the energy, and it can distinguish electron neutrinos. This is a picture of an electron neutrino in the experiment from a muon neutrino. You see that these are different pictures. So direction, energy, and flavor, and all of these things are important. So again, this is Earth. This is Japan, Super Kamiokande. Neutrinos can come from above or from below. Those that come from above travel 20 kilometers. Those that travel from below 10,000 kilometers. And because of the isotropy, if nothing happens to them on the way, the flux from above, the flux from below should be the same. And here are the results. So what we see here in the left is the flux of neutrino, the number of events of mu neutrinos as a function of direction. So cosine theta equal 1 are coming from above. cosine theta equal -1 coming from below, 0 coming from the horizon. And in red is the expectation if neutrinos are massless, and so the flux from above and from below should be approximately equal. In black are the experimental data of SuperK, and there is no deficit for neutrinos that traveled 20 kilometers, and there is a huge deficit for neutrinos that traveled 10,000 kilometers. Okay, and it grows with distance. So it seems that someone designed Earth, its size, and the atmosphere just to be sensitive to neutrino oscillations. It's really an amazing coincidence. And what we understand is that since there is this dependence on L over E, and when L over E is small enough, then there is no effect. Where it's large enough, there is a suppression. This is exactly what we are observing here. So assuming neutrino masses and the right parameters, the green line is the fit, and it's excellent fit to the data. Moreover, we can describe the probability as a function of L over E. Remember, it should be sinusoidal, and indeed, in blue is the expectation, and it fits very nicely the behavior that we expect from neutrino oscillation. So this is the discovery of neutrino oscillation.
Same data, Yossi? Just
Yeah, yeah, it's the same data, yeah. So, yeah, so that was atmospheric neutrinos. They oscillate when they travel. The typical energy is GeV. When they travel more than a few hundreds of kilometers, they already have enough time to change into tau neutrinos. Solar neutrinos. So for us physicists, the burning of the sun is that 4 protons become helium-4, 2 positrons, 2 electron neutrinos, and gamma rays, also known as sunlight. And what we are after here now is the electron neutrinos. As I said, they are wonderful messengers from the core of the sun. So we want to detect them in order to understand how the sun burns. Okay? Before we have pretensions to understand all the astrophysical events, we better understand the sun. And it's not that easy to do it. So one thing to remember is that the sun produces electron neutrino and only electron neutrinos, accompanied by positrons. This is the spectrum. These are experiments. SuperK also observed snow, homestake, which I'll describe, galaxy GNO. For an amazing reasons that I do not understand, this is a Nobel Foundation plot, and they omitted one experiment from this list, a Russian experiment. I have no idea why, but it has the same reach as the galaxy. So this is the spectrum, neutrino energy in MeV, and the flux. Just to understand how difficult this is to detect, at each second, on each centimeter squared of your body, 10 to the 12 neutrinos produced in the sun are going through. Each second, centimeter squared, 10 to the 12. If you volunteer to serve as neutrino detectors, and you devote all your life, 100 years, and you weigh 100 kilometers and try to stop them, on the average, you will stop 1. So this is how hard it is to stop them. So don't volunteer to this. You need bigger detectors than you. So the first experiment, a very bold experiment to detect solar neutrinos, started operating in 1967, led by Ray Davis, who got the Nobel Prize for 2002, and inspired and all the way accompanied by a theorist who was a friend of this department of Israeli physics, John Bacall. And what Davis did was he found a gold mine in South Dakota, put there a container, went I don't know where, and bought 150,000 gallons of cleaning liquid. And this, okay, I think it's here. Okay. So this cleaning liquid has chlorine in it. And what neutrinos sometimes do, very rarely, is to interact with the chlorine, make it an argon-37. Okay, 150,000 gallons of cleaning liquid have about 10 to the 30 atoms of chlorine-37. In a month, according to the calculation of John Bacall, 15 of these should convert to argon. Okay, so 15 out of 10 to the 30. Davis, each month, examined his 150,000 and looked for argon atoms, and what he found was 5. Okay, continuously over 30 years of operation, months after months, months after months, instead of 15, more or less 5. So the flux observed at the Homestack experiment compared to the flux of the standard solar model, the calculation of John Bacall, is 1/3, a third. And could it be the experiment? Would you trust an experimenter that tells you that he found 5 out of 130 and it's not 15? I don't know. I'm a theorist, but yeah.
How can you count 5?
Well, you look for the radioactive, so the radioactive decay, I think, of these, you put them in a trap and you look for the radioactive decays of the argon. So the sun, that I think was the main suspect for many years, because the particle physicists we are used to construct our sources, to manipulate them. It's a bit difficult to manipulate the sun, and we don't want to stop it for a while to understand what's the background, etc. And the flux of the neutrino depends at the temperature at the core of the sun to the 25th power. So a very small mistake in estimating the temperature in the core of the sun would make a huge mistake in predicting the flux. So really our community, particle physics, was highly suspicious of the result and thought, okay, it's wonderful that astrophysicists are predicting it to within a factor of 3. Okay? Until the mid-90s, you could find such statements in the literature by leading particle physicists. And finally, it could be an effect due to the neutrinos. So the definite answer came from the SNOW experiment, 1,000 tons of heavy water on loan from the Canadian government, put in a zinc mine in Canada, in Sudbury. And this deuterium, okay, so heavy water have deuterium instead of hydrogen. So deuterium, a proton and a neutron. And when a neutrino hits it, it can do two different things. It can convert the neutron to a proton, and then an electron is emitted. This is sensitive only to electron neutrinos. That can be done only by electron neutrinos. So this is a measurement of the flux of electron neutrinos. All the previous experiments measure the flux of electron neutrinos and nothing else. What this experiment was the first to do is the following. The neutrino could also hit the deuterium and just decompose it, disintegrate it to a proton and a neutron, and continue as a neutrino. And the experiment could observe these neutrons, and therefore this can be done by all neutrinos. This is a Z exchange. So this is a measurement of the total flux of neutrinos coming from the sun. So now we have two measurements, electron neutrino flux, total neutrino flux. And we can compare this. And what this experiment was first to do is to measure the total flux in all 3 flavors. And okay, this is a picture of experiment again. Okay, so this is the result. So here we see the flux of electron neutrino, and this is the flux of muon and tau neutrino. So the flux of this charge current, the W exchange, are only measuring the flux of electron neutrino, and it was here. The flux of the total flux measurement is here in purple, and the total flux was 3 times larger than the flux in electron neutrino. Okay, 3 times larger. So that tells us 2 things. First of all, undoubtedly, some of the neutrinos come from the sun. 2/3 of them convert into muon and tau neutrino. Second, Davis experiment was correct from the beginning. This 1/3 is exactly what is seen here. So the experiment was perfect. And third, in dashed line, is the prediction of John Bacall. Again, perfect agreement. So the theory of the sun, the experiments, all were perfect, and the blame is on neutrino. They changed their flavor on the way, or actually due to the MSW effect in the sun. Electron neutrinos become muon and tau neutrinos, and there is no doubt about it after this experiment. So this is another experiment doing oscillations with the same neutrinos that play a role in the sun. And again, you can see now it can be measured, the survival probability as a function of L over E. And again, you see this fantastic agreement with the sinusoidal behavior that is the prediction of theory, first, by the way, by Pontecorvo in 1957. So I have to put this, I know it's a hamburger chain that I will not name. They have a Happy Meal. All of these of you who are parents or grandparents know about Happy Meal. If you take your kids there. And Happy Meal in South America turns out to be called Cajita Feliz, which is a happy small box. Okay, but if you read this literally, it means, it says McDonald's and Cajita are happy. That's the translation. So this hamburger chain had some vision about what will happen in the Nobel Prize of 2015. Implications. So let me just mention that I worked on neutrinos for many years. My first paper is during my PhD with Chaim Harari, 1987, and 2 reviews on the implications of particle physics on cosmology, if you are interested. So this is what we learned from the 2 experiments. Okay? We learned numbers, not just the fact that there are flavor transition, that there is MSW effect in the sun and neutrino oscillation for atmospheric. We learned of 2 different mass squared differences. So if you looked at the equations there, they were sensitive to mass squared differences. And one of them is of order 10 to the minus 3 electron volt squared, the other 10 to the minus 5 electron volt squared. We also learned about the elements of this unitary transformation from flavor basis to the mass basis. So these are the numbers that we learned. And why is this important and significant? So for that, I have to tell you a few things about the standard model, which you know if you're a particle physicist, but maybe not if you are not. Mathematically consistent theory based on symmetry principle, really beautiful. It describes the strong, weak, and electromagnetic, and also now the Yukawa interactions. All of these, everything except gravity is described by this theory. It was first conceived in the late 60s and early 70s. So now it has a history of 45 years of experimental testing. Tens of thousands of data points were correctly predicted by the theory, something that even the fathers of this theory did not imagine would happen. Really a fantastic theory and very frustrating one, because experiment after experiment are being built by hundreds and thousands of people in order to invalidate the standard model, and we fail again and again. We just validate it. And in particular, the 2012 discovery of the Higgs boson, the Atlas CMS experiment, completes the missing piece of the standard model. We now know all the elementary particles. We've measured all their properties. In principle, we have a theory which might be valid up to the Planck scale, in principle. Let me mention that 2 days ago, there was an announcement in CERN, which can, I hope, we don't know yet. It may very likely is statistical fluctuation, but if not, then I will have to erase this transparency next year. I really hope that I will give here another colloquium where these statements turn out to be incorrect. So just to tell you how beautiful the standard model is, it's based on symmetry principle, and it is defined in 3 lines. I will not explain the 3 lines, but that's the full definition of the standard model. Okay? The standard model in full detail is here on this one transparency. It's really amazing thing that all of these tens of thousands of data points and 4 different types of sources and 12 elementary particles are described by just these 3 lines. It's beautiful. Now, one of the most striking things about the standard model is that you put in certain symmetries and a set of particles, and you get as a prediction an additional set of symmetries, which you do not put in. These symmetries are predictions of the model, and they correspond to conservation laws, which again, you did not put in. They come out as a prediction. And if any of these conservation laws is found to be violated in nature, then it's an unambiguous proof that the model is incomplete. And this is the symmetry, the accidental symmetry, and here are the result of some results, 3 examples of results of conservation laws that follow from this symmetry. So one is that the proton should be stable, and experiments like Kamiokande looked for proton decay, has not been observed so far. The lower bound is 10 to the 33 years. You should be impressed because this is 23 orders of magnitude longer than the age of the universe. So it's really a non-trivial. It's good for us, okay, that protons are still around. The muon should never decay into an electron and a photon. And this is the strongest upper bound on any branching ratio of any elementary particles. Out of 10 to the 12 decays, not even once it decays to an electron and a photon. And neutrinos should be massless. And here, by now you know the answer. Neutrinos are not massless. These 2 experiments have independently shown that neutrinos have masses. And this conservation law is violated. Actually, all these 3 symmetries have been shown by these 2 experiments to be not valid in nature. So that's what is so important about these results. It gives us the long-awaited proof that the standard model is incomplete beyond the fact that it does not include gravity. Okay? So this is something to do with particle physics. And this is the most important statement that can be made on the basis of these experiments. The standard model is not a complete theory of nature. That's the proof by these 2 experiments. That's why they are very, very important. We know much more than that. We understand that most likely the standard model is an excellent approximation to physics at the 100 GeV, which is the reason that most experiments are successful. And we can actually put an upper bound on the scale above which it is not valid. And this upper bound is quite far away from present experiment, 10 to the 15 GeV. But it's still a significant bound. So above 10 to the 15 GeV, the standard model cannot be a valid theory of nature. And the first thing about it, that this is 3 orders of magnitude below the Planck scale. Okay, so this is new physics, not just quantum gravity, but really new physics. It's also, in some extensions of the standard model, the couplings of the strong, weak, and electromagnetic interactions unify at about 10 to the 16 GeV, which leads to the whole idea of grand unified theories. This scale is extremely close to that, and we have reasons to believe that this is not a coincidence, but it has a significance. There is really, it's a further support to the idea of grand unified theories. And the simplest option is that what the standard model is missing are heavy fermions that have charges under none of the forces. No electric charge, no strong charge, no weak charge. So they could be arbitrarily heavy. They are insensitive to any of these 3 forces, but must have Yukawa couplings to the neutrinos that we see in the Higgs. This is how they, in the end, generate masses to the neutrinos. So this is what we are missing, probably. Let me just mention that this has also implications for cosmology, so not just for particle physics. One of the open questions in cosmology has to do with antimatter. All the structures in the universe are made of matter, protons, neutrons, and electrons. None is made of antimatters, antiprotons, antineutrons, and positrons. This is quantified by what we call the baryon asymmetry, the number density of protons and neutrons minus the number density of their anti, normalized to the number density of photons, is a number of order 10 to the minus 9. The standard model allows us to understand why the antimatter disappeared from the universe. But it also allows us to calculate how much matter survived in this. In the beginning, there were equal quantities of them close to the Big Bang, and now this is the situation. The standard model explains in principle how this transition went dynamically, but it predicts that the surviving matter is less than 1 galaxy. And we know that there are about 10 to the 12 galaxies, so the standard model fails miserably on this cosmological effect. And this is one of the most important questions in particle cosmology. And the interesting fact is that the same new physics that can explain why the neutrinos have masses, what goes wrong in the standard model, or what the standard model is missing, exactly the same ingredient, heavy singlet fermions that have Yukawa couplings to neutrinos and the Higgs, can generate this asymmetry of this size, can let much more matter to survive. This is a scenario known as leptogenesis, and it has to do with the decays of these heavy things into the light neutrino in the Higgs. So the Higgs is playing a role also in the survival of matter. So this is roughly why all of this is important. So let me just share a few final thoughts about basic research. We wanted to discover proton decay, and we discovered neutrino oscillations. They were the background to this, but led to discovery. Astrophysicists wanted to understand the sun, and in the end, we found the MSW effect, and again, neutrino masses. So these huge discoveries are by experiments that originally were not built for this purpose. And now we are observing and want to further observe neutrinos from Sternberg galaxies, gamma ray bursts, this GZK, the highest energy, cosmic neutrino background, the most abundant. All of these are still future things to see. Neutrinos never failed to surprise us. So all we can hope is that we will find surprises also in this and learn new things that we did not mean to. Thank you. This is
Just a very naive question. So in the superconductor experiments, the water was used.
Yes.
What is the nuclear reaction that leads to the detection of the neutrinos?
Okay, so what is happening is that if a muon, say, hits the protons or whatever, if it's a W exchange, it produces a muon. And this muon in the water is faster than light, so it creates a Cherenkov radiation. And the photomultipliers are observing this Cherenkov radiation. Similarly with electrons. And there is also some sensitivity to tau leptons, but less. Yeah. So the observation is of the Cherenkov light in the detector.
So you showed that from the neutrino oscillations we learn about delta M's, and why they are significant. And there were two other parameters, the mixing angles. Are they important? Did we learn something from their values?
Yeah. So, okay. So oscillations are sensitive to two parameters that have to do with the experiment, distance and energy, and two that have to do with particle physics, which is mass square difference and this mixing angle, this entry. Yeah. The mixing angles, they are also important. These are fundamental parameters of the theory, and actually. They were also one of the main reasons that the particle physics community was suspicious of the whole thing, because there is a similar phenomena of change from interaction basis to mass basis also in the quark sector. And there this rotation is small. All the mixing angles are small, and it teaches you something about prejudices in theoretical physics. So everyone expected these angles, also this rotation, to be a small rotation. The size of these angles is a question in physics. Okay, it's a topic to explore why they have the values that they have. And the thing is, in both phenomena, the mixing angles are large, order 1. The rotation is really a large rotation. Actually, for the atmospheric neutrinos, it's maximal. It's 45 degrees, which is okay. It's the two mass eigenstates are equal superposition of mu neutrino and tau neutrino. This was a huge surprise. It was a reason. I mean, if they were not large, the experiments would not have been sensitive. So it's another of these miracles. Okay, one miracle is the size of Earth. Another miracle is the density and the pace at which the density of electron neutrinos is changing in the sun. All of these really fits the values, makes them sensitive. It's really highly, non-trivial or surprising. And the third thing is that the mixing angles must have been large in order that we will observe the effect. And they are large only for this sector, not for the other sectors. So people were skeptic about it, and the fact that this rotation is large for the leptons and small for the quarks is very surprising. We do not understand it. It is not really consistent, or it makes you doubt of the Grad unified theory, which tells you that quarks and leptons should be similar. So it's something that we do not understand, but probably is a hint for something that we still need to explore. Done.
Great talk. Thank you very much.
Thank you.
How did the experiment in Italy, that some people, the Weizmann involved, fit into the evolution of this?
Yeah. So if there is one thing which is controversial about this Nobel Prize, is the fact that between the Davis experiment and so the first experiment was this. This is the Davis experiment. Then came SuperK, and then before SNOW, there were experiments in Italy, Galex, and in Russia, SAGE, which use. So Homestake is a conversion of chlorine to argon. These two are gallium and germanium. So gallium in the target is gallium, and it's and indeed Dostrovsky of the Weizmann Institute was the chemist that allowed the extraction of the germanium out of the sample to show how many converted. And they made an important step because, as you can see, they are sensitive to much lower energy of solar neutrinos than the other experiments. Now, the sun is built even in a more sophisticated way to allow us to understand things. The fact if it goes MSW effect or oscillations between the sun and the earth depends, among other things, on the energy. And it turns out that 1 MeV is roughly, if you are above 1 MeV, it's purely the MSW effect. If you are well below 1 MeV, it's almost purely neutrino oscillations in vacuum. And so actually we are able to see both phenomena in the sun, but not the original experiment. And so these ones did a combination of these two, which means that the suppression is milder. It's not 1/3, but say 0.6 or 0.50 something. And that's what they saw. And so from the fact that this experiment sees 1/3 and this one see about 0.6 suppression of the flux of electron neutrinos was already a good part of the way to prove that this has to do with neutrino features and not with the sun or with the experiments. And so this is the contribution of the gallium experiments. Very important, made a significant step towards discovering that this is neutrino masses that is what making the effect.
Next question.
Are there other predictions that come out from the seesaw mechanism that can be solved at the LHC?
The short answer is no. So the particles that we are missing are probably very heavy, orders of magnitude, on the simplest scenario, orders of magnitude above the reach of the LHC, and they carry no charge at all, not even weak interaction charge. So they are beyond the kinematic reach and beyond the sensitivity, or have no sensitivity of any of our detectors. That's in the simplest scenarios of the seesaw mechanism. If they are to play a role in the leptogenesis scenario, and also for other reasons, then probably we'll see circumstantial evidence for it, but in other experiments, not in the LHC. We should see something called neutrinoless double beta decay, which would be a proof that neutrinos are Majorana particles and not Dirac fermions. And we should see CP violation in neutrino oscillation. So say the probability of Ni-mu to Ni-e transition can be different from anti-Ni-mu to anti-Ni-e. That's in log baseline experiments where the source is an accelerator and the detector is hundreds or thousands of kilometers away from the source. So these are two things that would tell us that the mechanism that we are thinking about is correct one, would give further circumstantial support to the idea this is the source of the baryon asymmetry. A direct detection of these extra degrees of freedom is highly unlikely in the simplest scenarios. So, yeah.
Thank you.